So take a peek at my very first series. We still classify this as series, but in reality, it's just an infinite sum. Notice, however, each and every one of these terms are mere constants. Now, it may be true that the second example is a series, but notice what's so instinctively different from it than anything else we studied so far. When it comes to its explicit formula for the nth term, or when it comes to these terms expanded out, it is the case that I have a variable expression in each of these terms. So I sometimes subclassify this as not just simply a series, but a power series because of that factor in the nth position involving x. Now here too, I have a power series because the explicit formula for the nth term involves some factor of x to some natural number power or non-negative integer power. As a matter of fact, in the expanded form, notice that each and every one of these terms involves a factor of x raised to some power that's non-negative integer. That's x is 0 power, 0 is non-negative. Now, if it's the case that what's being raised to the nth power is x minus some number a, then I refer to that a as the value of x about which I have a power series expansion. And so here I've got a power series expanded about x equals 1. Here I got a power series expanded about x equals 0. I know I have not addressed the question, which is who the HECK cares, but I'm getting there. Now, it is the case that with a series, how about I'm taking this one? It will be the case that for some values of x, this may converge, but for some values of x, it might not converge. And when it comes to the values of x for which it does converge, I might refer to that as a domain of this function, because this really is the output of the function. And if a function does have a power series representation, I sometimes say that that function is analytic. Now, going back to what I said about how for some values of x, a series might converge, for some values of x, it might not, then only one of three possibilities can occur. Number one, given a power series like this, it might be the case that it converges for all real numbers x. If that's the case, I sometimes say the interval of convergence is this, and the radius of that convergence, well, the radius of that interval of convergence is this. It could be the case that the power series can converge for no values of x, with one exception. If x is equal to a, I don't care what else is going on, it's always going to converge. So it might be the case that it only converges at x equals a, in which case I say the radius of convergence is 0, in which case I say the interval of convergence is, if you don't mind me saying it this way, that singleton set. Now, the more complex situation is that this power series converges for all real numbers between a minus r and a plus r, where r is some fixed constant. On a number line, wouldn't that look like an interval of radius big R centered about x equals a? In which case, I might say that the radius of convergence is r. But the interval of convergence is from here to here, but it might be the case that I include one or two of the endpoints. Those are the three case scenarios.